Okay, so 15.2 covers double integrals over general regions. So 15.1, we looked at how to calculate a double integral and what it meant, but we looked at rectangular regions. So I'm going to give us a picture of what we did in 15.1 and a picture of what we are doing today. So here was the idea in 15.1. You had some surface, let's call it z is some function of x and y. And if you remember, we looked at some rectangular region R in the xy plane. And what we did is we mapped that region R. Okay, it's kind of off the figure, but you get the point. We mapped it up to z. And what did the double integral calculate for us? Volume. Do you remember that it calculated the volume between our surface and the xy plane? Okay, here's what we are doing today. It's still the volume problem. We still have some surface z, which is a function of x and y. Here's the difference, which makes things much tougher. R is no longer a rectangle. R is going to be some different figure. And then it's the same general idea. You're going to map R up onto your surface, and then you're going to calculate the volume between your surface and R. But as soon as R is not a rectangle, things get much trickier. Okay. So first thing we need to know is that there are two types of regions R, not including the rectangle. The rectangle is one type. And then within these general regions, there's two types, aptly named type 1 and type 2. Okay. And again, these are regions in the xy plane. Here's the idea with type 1, or here's what type 1 looks like. Type 1 has two vertical boundaries. One is x equals a and x equals b. And then the top two boundaries are functions of x. Type 2 region is the other way. You have two horizontal boundaries at y is equal to two constants, y equals c and y equals d. Your vertical boundaries are then curves that are functions of y. The type of R that you have will determine how you set up the volume problem. So when we did 15.1, where we had a rectangular R, we talked about it doesn't matter if you integrate with respect to x or y first. And then we talked about sometimes it's easier one way or another. That's not going to be the case now. Now it's going to be specifically, it's much easier to integrate one versus the other. If you have a type 1 region, if you're looking at double integral over the region R of your f of xy, here's how that's going to look. It's still the double integral of f of xy. Whatever your constants are, that's what you integrate last. So in this case, the upper and lower boundaries for y, those are functions, so we want to integrate with respect to the functions first. So your lower and upper boundaries for y are actually going to be functions, not constants. For a type 2 region, it's going to be a similar idea. The constants are always what you integrate last. So we have y is a constant, so we will integrate with respect to y last. We will do x first. X is those two functions, so our inner limits will be functions of y, not constants. Okay. This is going to involve a little bit of trial and error. So for me personally, I don't look at each and think, okay, do I have a type 1 or a type 2? I try to set up the limits. So that's what we're going to do. We're going to do a few examples where we set them up. We're going to do a few examples where we actually solve. And as you guys do more problems with this, you'll get better at it. So let's try one. We are going to evaluate double integral over the region D. That's just R, just using a different letter. Our function is going to be x plus 2y, bless you, dA. And then our region D is going to be the region that is bounded by y equals 2x squared and y equals 1 plus x squared. Okay. First step is always to draw a picture of your region. So I don't mean draw a picture of this function, I mean just the two-dimensional region. So before I called it R, now it's called D. That's the first thing I want us to do is draw that region. So y equals 2x squared. It's going to look something like this. 1 plus x squared. It's going to look like this. Okay, so the region that we are referring to is this region right here. Okay. Here's my suggestion to you. My suggestion is forget about the type 1 and type 2. I don't think they're very helpful. What I do is I look at my region and I look at if I integrate one way, what happens? If I integrate another way, what happens? So we're going to set up our limits. We have to figure out, do we integrate with respect to y first or x first? So here's what you're going to look at. If I integrate with respect to y first, I'm going up and down. No matter where I am in the region, is the lower bound always the same, and is the upper bound always the same? Function, that is. Yes. Okay. If I go left to right, no matter where I am in the region, is the left function always the same, and is the right function always the same? Do you notice if you're down here, you go from this function to this function, but if you're up here, you go from this one to this one? That changes. We don't want to go left to right first then. We want to go up and down first. Because top, always the same function, down, always the same function. Okay. This bottom function is that y equals 1 plus x squared. So that is our bottom limit. Our upper function is y equals 2x squared. Those are in terms of y, so we are integrating with respect to y first. Brian?
Why is 1.1 plus x squared the bottom if it's on the top? I think it's on the top.
Because I have them backwards. Thank you. Sorry, guys. Thank you for saying that. Okay, that looks better. Thank you. Now we need to integrate with respect to x first. Your outer limits are always constant. So leftmost point has an x value of -1. Rightmost point has an x value of +1. This then is what we're going to be integrating. So we're going to integrate exactly the same as we did in 15.1. We're going to do the inner integral first. So you're going to integrate with respect to y first. So if we integrate with respect to y, we get xy plus y squared. We're integrating from y equals 2x squared to y equals 1 plus x squared. Remember I suggested to you that you write y equals so you know what you're substituting in for. So this then becomes x times the quantity 1 plus x squared plus 1 plus x squared minus x times 2x squared minus 2x squared dx. So you guys see how I got all of those? Okay, I would like to tell you that there's like some nice way to do this, but you have to multiply everything out and combine all the like terms. I'm fairly confident you guys could do that, so can I just tell you what it ends up being? Okay, ends up being negative 3x to the fourth, subtract x cubed, add 2x squared, add x, add 1 dx. Now it just looks like it normally would. Okay, so now we're gonna integrate again, this time with respect to x. So we get negative 3/5 x to the fifth minus 1/4 x to the fourth, add 2/3 x cubed, add 1/2 x squared plus x. Evaluating from x equals -1 to x equals +1. If you trust me, you get 32/15. Okay. At this point, on your website, I don't care if you use a calculator, but I will tell you right now, you will not get a calculator on your test. So, I'm sorry, I'm not the one that makes that decision. For your final, Eastern doesn't let you use a calculator, so that's what we're going to do for our tests. Do we get the general gist of how to evaluate these? Okay, in my opinion, the setup is significantly more difficult than solving. So I would like to focus more on us setting these up. The solving you'll figure out. Next example we're going to do is we're just setting up. So we are going to evaluate double integral over the region R of x, y, dA. R is the region bounded by y equals negative x plus 1, y equals x plus 1, and y equals 3. Okay, so with the last example, we're going to approach this the same way. Start by drawing out that region R. Okay, this is the region that I got. You guys agree? Okay. It can be very misleading sometimes to look here. So if we look here, a lot of people are going to think, well, I'm going to integrate with respect to y first because all the functions are in terms of y. Sometimes that's the case, sometimes that's not the case. Again, look here. If we go up, down first, is the top function always the same? Is the bottom function always the same? No. If we go left, right, is the left function always the same? Is the right function always the same? Okay. So in this case, we want to integrate with respect to x first. We want to go left, right. We could integrate with respect to y first. That would be fine. If we integrated with respect to y, though, we would need two integrals. We would need one for over here and one for over here. Does that make sense? And sometimes that's going to be the case. Sometimes you can't avoid that. Bounds for y are going to be the easiest, so let's do those first because they're constants. The bottom value of y is 1. The top y value that we hit is 3. Okay, the left boundary is that y equals negative x plus 1. Has to be in terms of x, though. So it has to be some function of y. It has to be x equals. So if you solve for x, you get 1 minus y. That is your lower bound then. Your right function is that y equals x plus 1. Has to be x equals though, so again, solve for x. So then this would be your limits of integration. Okay. How do we feel about this? Okay. Am I right in saying that the type 1 and type 2 is not very helpful? Okay. I think you guys need some practice setting these up. So the next one I'm going to give you 2 or 3 minutes just to set it up. Does that work for us? Okay, you are going to find the volume of the solid that lies under z equals xy, above the region D, where D is the region bounded by y equals x minus 1 and y squared equals 2x plus 6. Okay, I'm going to start you out, but then you guys are going to find the limits. If we want volume, that's going to be the double integral over the region D of our function, which is xy, and then dA. So you're going to have to figure out the limits, and you're going to have to figure out if you're integrating with respect to x or y first. We're going to draw the picture together, and then you guys will go from there. Okay, y equals x minus 1, you guys know what that looks like. Y squared equals 2x plus 6. Do we know what that looks like? What shape is it? Let's start with that. Parabola, opening sideways. If you plug in an x value of -3, you get y to be 0. So that's your vertex of your parabola. And then it'll open sideways. Okay, so here's what I want you to do now. I'm going to give you 2 or 3 minutes. Talk to someone next to you. First thing I want you to decide is, are we integrating with respect to x or y first, and then find your limits. I want you to do this with someone, though. Don't do it individually. So turn around, make friends with someone next to you.
So which one do we go on? I feel like if the pattern when we just like
Okay, do we have a setup with limits? Almost, like another minute and we will? Okay, in a minute we're going to check in, go over the setup, and then you guys are actually going to calculate the integral. Okay, let's look up here. Did we decide we wanted to integrate with respect to x first or y? X. Okay, are we all confident on why it's x?
Yes.
Okay, so next thing that you should have done is you should have solved both of these to get them in terms of x. Did we do that? So we switched them both to be x equals. The leftmost bound is this parabola. If you solve for x, that ends up being x equals 1/2 y squared minus 3. Rightmost bound is this line. If you solve for x, it ends up being x equals y plus 1. Okay, then we need to know the lower bound for y and the upper bound for y. Did you all, it sounded like you guys figured out we needed to find these two intersection points. Did we do that? Okay, this top one is the point 5,4, and the bottom one is the point -1, -2. Did we all get that? Do we want to talk about how to find those, or we're...
Can you go to y plus 1 on 1/2 y squared minus 3? How you got that?
I solved both of these for x. So added 1 over this one, subtracted 6 divided by 2. Is that enough? So then we should have gotten from -2 to 4. How many people got that? Great. Any questions? Okay, you guys do at least have to go through one of actually calculating these. So I'm going to give you like 3-4 minutes now to now go through actually calculating this volume. Good luck. should be some squaring and binomials. Do we have any answers yet? When you are ready to look up here, or if you want to check where you are, my work is at the front.
I took out one more. How did you get 36 from that?
36? Wait, where's the word?
She did it in her head.
Okay, so when you get to here, like use your calculator, that's fine. I will not give you something like this on your test.
Oh, okay.
So I will give you something that's much more reasonable to work with. Okay? But my concern was, did we get the gist of this right?
Yeah.
Like dropping a negative or a constant, that's not a big deal to me, but did we understand the process of how to go about this?
Yeah.
Okay.
No, I don't know. I didn't take up one half.
Okay. Any questions on this before we go on to the next things we need to talk about? Okay. This is kind of the idea for the rest of the chapter. So we're also going to get into triple integrals with this same idea. So it's really, really important that we know how to set up the limits. Because if you set up the limits wrong, you're toast for the rest of the problem. Brian, are you okay?
Every time I forget to do integrate x first, so I did the whole thing wrong.
I mean, this is new. So if you keep doing it So, moving on. Next problem. This time I'm going to be kind, and I'm going to give you the limits. Okay. So this time I'm telling us to integrate with respect to y first and then x. What's the issue? Do we know how to integrate sine of y squared? No. Okay, so another idea from this section is we need to be able to reverse the limits or to switch the order of integration. So what we're going to do is we're going to integrate with respect to x first and then y. That does not just mean you get to switch those. Okay, so here are the skills that we need to have in order to approach a problem like this. First thing that we need to do is we need to be able to draw the region based off of those limits. Next thing you have to be able to do is reverse the order. Okay, so here's the idea. If we look at the inner limits first, these are the limits for y. So we are going from y equals x to y equals 1. Okay, so that's what we're going to draw. This is our y equals 1, and this is our y equals x. Then we are going from x equals 0 to x equals 1. X equals 0 to x equals 1. So this is the region that we're looking at. Okay, so in this case, top and bottom limits are constant. Left and right limits are constant. So it really isn't easier one way or another, except that we can't integrate y squared or sine of y squared. So we are going to integrate with respect to x first and then y. If we look at the limits for y, what is the bottom limit for y? So this is the lowest point for y. What is y here? 0. And then it goes to 1. For x, so our inner limits, we're going left to right. The left function is x equals 0. The right function is y. Okay, so then we're going to do this one. Integrate with respect to x first, so we end up with x times the sine of y squared. We're evaluating from x equals 0 to x equals y. So we get 0 to 1. If we plug in y, we get y times the sine of y squared. And then we get 0. Now this should be much easier to integrate. So you can do u substitution if that's what you need to do, or you can do it in your head. Should end up being -1/2 cosine of y squared, evaluating from y equals 0 to y equals 1. Are you guys okay that I just did it without the... So this ends up being -1/2 cosine of 1 minus -1/2 cosine of 0, which is -1/2 cosine of 1 plus 1. So on your web assignment, I don't know if it specifically tells you you need to reverse the order. But if you don't know how to integrate what you're already given, if you can't, that's one option, is to reverse the order. Okay, we have one last thing to talk about. Questions on this? Okay, great. Last thing we need to talk about. So far, we've been using double integrals to calculate volume. You can also use double integrals to calculate area. So that's the last thing I want to talk about. Okay, so let's sketch ourselves a little picture. Let's say that we're at z equals 1. And we have some region R that we're mapping up onto that z equals 1. We can all agree that the general idea with volume is that you are calculating the area of the base, and then you're multiplying it by the height of the figure. And that gives you volume. In this case, the one that I drew, what is the height of our figure? 1. Because we're at z equals 1. So this is the special case where volume is actually equal to area. So this is volume using a double integral. And that's an R. We want that to be equal to the area of R. And that'll be the case when z is 1. So if you take the double integral over the region R of 1 times dA, that gives you the area of R. Okay. So we're going to look at one last example. We are going to use a double integral to find the area of the region enclosed between y equals x cubed and y equals 2x, specifically in the first quadrant. Okay, so first thing we need to do, obviously, draw a picture. So that's our y equals 2x. As our y equals x cubed. Y equals x cubed, though, doesn't go through that point. That's just a poor figure. This is the area that we are calculating. So we're going to do a double integral over the region R of 1 times dA. We need to figure out if we're integrating with respect to x or y first. Okay, is the top function always constant? Is the bottom function always constant? Okay, left function, right function? Yeah, so in this case, doesn't really matter. I would suggest that you integrate with respect to y first. Why would I suggest that? Yeah, both functions are already y equals. So I would suggest that you do y and then x. That's just my suggestion. Our bottom limit for y is x cubed. Our top limit for y is 2x. Okay, and we are going to have to find this point of intersection. That one is just x equals 0. So if we set that x cubed equal to 2x, factor out an x, we get our x equals 0, which we already knew, and then plus or minus root 2. So at this point, x is root 2. So that would be your upper limit.